extracting root modulo a given number. We started talking about it last time, and I managed to confuse myself in you. So let me try to repeat it and maybe put more examples where the thing works, where it doesn't work, and trying to explain exactly what it doesn't work. So recall what the problem is. The problem was try to solve an equation of this type. So usually I say it's a congruence. It's not an equation of integers, it's only an equation about remainders modulo a given number. So the question is how to solve such a congruence. And I try to explain it in some particular cases, this congruence has exactly one solution and it can be easily found. So let me once again try to formulate what we can do. So the idea is as follows. If you have any number, the idea, the main thing we're using, yes, it is idea. If you take any number and raise it to some power modulo n, well, it seems that it actually depends on this number n. Well, that's of course right, but isn't the full truth. The full truth is that it depends not quite on m. If a is relatively prime to n, this thing depends only on m modulo 5n. So this thing depends, well, not quite on m, but rather on m modulo 5n. Well, if GCD of a and n is equal to 1. So that's the main observation. Once again, what's written here is that suppose that you are given some number which is relatively prime to n. And you want to compute what is this power raised to some power modulo n. Well, the claim is that the result of this computation doesn't quite depend on m. Well, it does depend on m, but you don't need to know m exactly. All you have to know is what is the remainder of m once you divide it by phi of n, by the order function of n. Well, that's pretty much the same as reformulating Euler's theorem. So the explanation for this step is n to the power of phi of n is order into 1 modulo m. So a to the power of m plus any multiple of phi of n is congruent to a to the power m modulo m. So that's very easy observation. It's just a reformulation of Euler's theorem. Now, what does it tell you about this equation? Well, if in this equation, so corollary, this observation is as follows. If x to the power k is congruent to b modulo n, well, and some conditions. One condition is that this number b is relatively prime to n, and you also can invert this power k modulo phi of n. So n k is invertible modulo phi of n. What it means is, well, it just means, we know that it just means that GCD of k and phi of n is also equal to 1. So suppose that this holds. Then, so in this case, you can compute its inverse modulo phi of n. Let's then if S is K, let's say K is congruent to 1 modulo 5m, let's say that with the condition that K is invertible modulo 5m. So then for such an S, the following identity holds. If you want to find out what X is, you can just say that it is, well, the same as X to the power of Sk, because, well, there's this statement. If you want to raise X to some power, you don't have to know this power exactly. All you have to know is what is the remainder once you divide by 5n. The remainder of Sk is the same as 1, so X is the same as X to the power Sk modulo n. And this is just V to the power K, V to the power S modulo n. So that's a corollary about extracting case roots. So once again, what can we do? The corollary tells you the following information. Suppose you want to extract case root out of number b. And suppose you know that this number b is relatively prime to the modulus n. Well, then you can do it as follows. You can compute 1 over k modulo 5n, so in the sense of the inverse of k modulo 5n. And then to find x, you just raise d to this power 1 over k. The only conditions which should hold is, well, this condition, and the other one, 1 over k, does exist modulo 5n. So it's this condition.
Excuse me.
Yes.
Could you explain invert more? That means it's not theorem model, right?
No, not quite. So invertible, let me recall what is invertible. You fix some modulus n, and you ask what residues are invertible modulo this modulus. So we want, well, we fix some, in this case it was k. Let me translate this. So a residue A is invertible for some number n, if once you find b such that a times b is equal to 1 modulo n. So that's what it means being invertible. Just the usual definitions. There exist some other modules, such that once you multiply by our modules, you get 1.
Theorem model clearly not invertible.
Sorry?
Theorem model.
0 is not invertible. You can't divide by 0. But there are many other numbers which you cannot divide by modulo. So, for example, modulo 12, you cannot divide by 2. And in general, we have characterization. A is invertible modulo n if and only the GCD of A and n is equal to 1. So all the numbers which are relatively prime to n are invertible. All those which are not relatively prime to n, which share some common factors, they are not invertible modulo n. And basically, that's very simple characterization. You can prove it quite easily using the linear quantum equations. So what this equation means is that, well, I can try to explain. It's really simple. So how do you find inverse of A? It means that you should solve such an equation. So x is the inverse modulo n, if and only if x is congruent to 1 modulo n, if and only if k times n for some n for some k, which means if and only if, so the inverse exists if and only if the equation ax minus k times n is equal to 1 is solvable. And we know where it is solvable. Exactly when GCD of a and n is equal to 1. Right? Is it okay? Okay, so let me continue with an example, and then we'll see that these extra conditions are actually necessary. You can't just forget about them. You have to actually check them every time you try to apply this color. So let me try an example. So, in equation like this, congruence like this. X cubed is congruent to 4 modulo 33. Well, first of all, what is important about differentiating modulo 33 is to know what is phi of 33. You just know that it's, well, extremely important. So first step is compute what is phi of 33. In this case, it's very easy. 33 is 3 times 11. So it is 3 minus 1 times 11 minus 1. So it is 20. Next step, we verify that we can apply this corollary. So corollary, well, let me formulate this way. For GCD 4 and 33 is equal to 1. And 3, this is 1, is invertible modulo 20. So 3 is invertible modulo 20. Well, first of all, it's invertible because of general principle. 3 is relatively prime to 20. But we are actually interested in finding the inverse. So what is the inverse? Well, yes, it is 7. So what we want to find is some number, 3 times some number, should be congruent to 1 modulo 20. And it is pretty easy to verify that such a number is just 7. I mean, you can of course actually solve it using the general algorithm for solving linear equations, and we did it at one point in the course. But let's not stop right now. So we know that 3 inverse is 7 modulo 20. Well, what do we have to do now? We take this equation, thus this equation implies that x, which is x to the power 1, which is x to the power 3 times 3 inverse, which is 7. We know that right here we are using Euler's theorem. We know that x raised to the power 20 is always equal to 1. So we think it is the same as 4 to the power 7 modulo 33. So here we are extracting root. We are raising both. Well, in a way, we are raising both sides to the power 1/3. The meaning of this procedure of raising to the power 1/3 is exactly this one. 1/3 should be interpreted as the inverse of 3 modulo 533. Oh, and now it actually works. And the last step is just compute what it is 4 to the power 7. And that's not very hard. 4 to the power 7. Let me write it like this. It's 4 times 4 to the power 6. 4 cubed, I remember, is 64. So it's 4 times 64 squared. 64 modulo 33 is minus 2, because 66 is divisible by 33. And this is 16. And now, if you want, you can actually verify. Verifying an answer is much simpler than actually finding it. So, verification. If you take 16 and raise it to the power cube, it's the same as 4 raised to the power 6. And we just computed it with 4 to the power 6. It is minus 2 squared, which is 4. Modulo 33. So to verify that the solution is the right one is pretty easy. Just raise the solution to the power 3. To find out what is the solution, well, it was a little bit more complicated. You had to raise both sides of this equation to the power 1/3, interpret it correctly. Interpret it in such a way that actually you get very congruencies at each step. So maybe any questions about this example? So that's a typical example where this corollary works just perfectly. This number is relatively prime to this number. The exponent is relatively prime to 5, this number. Yes?
Do you mean mod 33 at the top of the other?
Yes. Mod 33. Yes, yes. 33, yes, thank you. So I have to invert only the exponent modulo 5m, and all the rest is modulo 1. Okay, so let's try examples where this doesn't quite work. So such an example. X cubed is congruent to 6 modulo 35. Once again, the question is find all possible x. Well, we begin in the same way. We compute what is 535. 535 is the same as 5 of 5 times 7, which is 4 times 6. So it is 24. And now we've got a problem. This exponent 3 is not invertible modulo 24. So 3 is not invertible modulo 24. So this operation of taking x and finding the cube of it has no inverse in this sense. There is no way to go back from x cubed back to x. And you'll see that there is a good reason for why there isn't any inverse operation. Also, how do we proceed? Any ideas? I mean, we still want to find the x for all possible x's.
I need to remember again, bring 35 into 5 and 7 up.
Yes. So here we have a complicated congruence modulo 35. Maybe let's try to break it apart to two congruences. One modulo 5, another one modulo 7, and then combine the answers using Chinese remainder here. Okay, let's try it. Let's indeed try it. So, idea, choose this remaining solution. So we will first solve x cubed is congruent to 6 modulo 5 and b. So these two congruencies. X cubed is 6 modulo 5 and x cubed is 6 modulo 7. We know that by Chinese remainder theorem, these two congruencies are exactly the same as this one congruence. So these two congruencies are much more pleasant because we can solve them by just trying all possibilities. There aren't that many. Here we have 5 remainders, here we have 7 remainders. Just let's try all of them. Maybe even if we don't have to. In the first example, so x cubed is congruent to 6, which is the same as 1 modulo 5. Well, in this case, 3 is relatively prime to 5 of 5. So 3 is inversible mod 5 of 5, which is 4. So to find what x is, well, we know that there will be only one answer. And one answer is always x equal to 1. So x congruent to 1 modulo 5 is the only solution. Sorry, I wanted to apply my corollary, but I had to verify another thing, that this number b is relatively prime to n. So n1 is relatively prime to n. Hence, x congruent to 1 is the only solution. X congruent to 1 modulo 5. Alternatively, you could just compute what is 0 cubed, it's 0, 1 cubed is 1, 2 cubed is 3, 4 cubed is -1 cubed, so it's -1. So only one works. Either way, you get only one solution. For the other part of the problem, x cubed is congruent to 6. It's better to rewrite it as -1 modulo 7. Well, here we cannot apply the same reasoning. 5 of 7 is 6, which is not relatively prime to this exponent 3. But we can apply the other reasoning. Just try all possibilities. So 0 cubed, 1 cubed, 2 cubed, 3 cubed, -1 cubed, -2 cubed, -3 cubed. Let's compute. 0 cubed is 0, 1 cubed is 1, so it's not good. Well, but -1 cubed is -1. So here we have one solution. 2 cubed is 8, which is 1. Not a solution. But -2 cubed is -1. So it is a solution. Finally, 3 cubed, 27 modulo 7 is -1, because 28 is divisible by 7, and -3 is not. -3 is cubed is 1. So this whole thing is modulo 7. So here, x is 1. I'm sorry, it's -1, -2, or 3. Modulo 7. So we got the following information out of this. X is congruent to 1 modulo 5, and x is congruent to either -1 or -2 or 3 modulo 7. So now we have to decide what is x modulo 35. So once again, x is congruent to 1 modulo 5, x is congruent to -1, -2, 3 modulo 7. And the question is, what is x modulo 35? Once again, we can apply, well, we can solve linear congruencies, but once again, let's try just this. So if x is 1 modulo 5, it could be, well, 1, 6, 11, 16, 21, 26, 31, that's it, modulo 35. So these are all the numbers which are equal to 1, congruent to 1 modulo 35, modulo 5. Which ones of them have remainder of -1, -2, or 3 modulo 7? Well, 1 is not good, 1 modulo 7, 6 is good, 11 is, what is it? It's 4, it's not good. 16 is 2, which is not good. 21 is divisible by 7, 0. 26, yes. 31, yes. Okay, so we have the following pairs. 1 minus 1 gives 0. 6, 1 minus 2 gives 0. 26, and 1, 3 gives 31. So here are the solutions. So x is congruent to 6, 26 for 31 modulo 35. So there is a reason why this operation of taking a cube of a number modulo 35 is not invertible. This operation just groups together different x's. It sends 3 different x's to the same answer 6. So you just have no chance of finding this consistent cubic root here. There's no way. This operation is not invertible. Well, let's try a different example. So this. So this. Yes. So what this means is that you cannot, well, so what it means? It means that you can solve this equation, which means we'll just find all possible solutions, and basically that's the way. Modulo some of these things you have to apply basically just exhaustion. You just exhaust all possibilities and find answers. You'll learn slightly better ways later. Oh, kind of slightly better ways, not much better ways. And well, it just means that sometimes such an equation, well, in the case when this exponent is not relatively prime to this modulus, such an equation might have, well, kind of unpredictable number of solutions. It could have no solutions, for example. It could have quite a lot of solutions. It could happen that all of the numbers modulo n are solutionable almost. So maybe let me give you a kind of stupid example. Example, equation x to the power 4.624 is congruent to 1 has modulo 35. How many solutions? Well, it happens that 535 is just exactly 24, right? So how many solutions does such an equation have?
All but zero.
All but zero? Well, almost.
All co-primes of 35.
Yes. So we know by Euler's theorem that this equation, well, any residue which is relatively prime to 35 raised to the power of 535 will be equal to 1. So all the residues which are relatively prime to 35 will be solutions. On the other hand, all residues which are not relatively prime to 35, which means those which are divisible, say, by 5. If you take a residue which is divisible by 5, raise it to any power, you get something which is divisible by 5. So no way to get 1. Same about divisibility by 7. So this equation has 535, which is 24 solutions. So you see, such an equation could have just quite a lot of solutions. What happens if it doesn't have any solutions? Here's another example. X to the power 24 is congruent to 3 modulo 35. Has no solutions. So maybe somebody can explain this way.
No x can't be co-prime, or otherwise it would be a co-prime for 35, or otherwise it would be 1, so it has to be divisible by 5 or 7, but 35 times k plus 3 is not divisible by 5.
Yes, exactly. So indeed, if x is relatively prime to 35, x to the power 24 is equal to 1. If x is divisible by 5, then x to the power 24 is still divisible by 5, but 3 isn't. And if x is divisible by 7, x to the power 24 is divisible by 7, but 3 isn't. So, explanation, if GCD of x and 35 is equal to 1, then x to the power 24 is congruent to 1 modulo 35. If GCD of x and 35 is equal to, well, if 5 divides x, then 5 divides x to the power 24, and if 7 divides x, then 7 divides x to the power 24. None of these possibilities is compatible with this condition. Okay, finally let me give you one more example, or rather non-example. We'll solve x cubed is congruent to 4 modulo 2. So once again, if you try to apply general thinking, we first compute what is phi of n. It is, well, how many numbers can share a common factor is 8. Well, it should be 2 cubed minus 2 squared. Or other way, it's just all odd numbers from 0 to 8. There are 4 of them. This exponent is invertible modulo 4. Well, 3 is invertible modulo 4. In fact, 3 times 3 is equal to 1 modulo 4. But that's not good enough. We cannot apply Euler's theorem. But 4 is not relatively prime to 8. So the corollary doesn't apply. Just you can't expect that raising this number to some power depends only on this power modulo 4. It just is wrong. This number raised to the power of 4 is not congruent to 1 modulo 8. Moreover, so the corollary doesn't apply. Moreover, this equation actually doesn't have any solutions. Maybe somebody sees some simple reason why it doesn't.
If x is even, this cannot have a not 4.
Yes,
If x is odd, then the left side will become to be odd. Well, right there.
yes. So indeed, if you know that x cubed is equal to 4 modulo 8, it means that x cubed is 4 plus some multiple of 8. It means that x cubed is at least even. But if x cubed is even, x is even. But then x cubed is actually divisible by 8. So it can never be 4 modulo 8. In fact, this equation has no solutions. And the explanation, write it down. X to the 4 equals x cubed is congruent to 4 modulo 8, then 2 divides x cubed, hence 2 divides x, hence 8 divides x cubed. Hence, x cubed is congruent to 0, modulo 8, and or if you're lazy to think about such things, you can just exhaust all possibilities. Once again, it's very easy. The modulo 8 is pretty small here. So both conditions are actually important. The fact that exponent is relatively prime to 5n here, and that this the result, the coefficient b here is also relatively prime to n. Both conditions are important. Okay, so maybe any questions about this root extraction? Okay, so the last thing I want to discuss today is an application of this to cryptography. The basic problem is like this. You have a message and you want to send it to somebody secretly. You don't want anyone who intercepts your message to be able to decipher this message. So it looks like this. I have two people. One is right here. Somebody is here. Somebody else is here. And this guy has figured out something extremely important. He's figured out the answer to the most important question, and it turns out to be 42. And now he wants to send this number to here. The problem is, well, he will be sending this number, but he doesn't want anyone who will be able to see this, whatever he sends, to be able to, well, decipher what is the meaning of this number. So the idea is like this. The guy right here, well, prepares a lock and a key. So he takes a key and he throws out the lock into the lock. Well, what happens next is this guy takes this lock, takes this number, well, puts it in a box, puts the lock onto this box, and sends it to the open, and waits for this guy to pick up this box. Well, if this guy picks up the box, he can open it. If somebody else picks up the box, well, he got box with a lock on it. That's kind of, well, a hard problem if the lock is good. If the lock is not good, well, you can just break the lock. So the problem is how to manufacture a good enough lock. And what are the properties of this lock? This lock must be somewhere in the open. Everyone can be able to look at this lock, to, well, look what is the mechanism of this lock, to be able to do whatever he wants with this lock, and still not be able to figure out how to open it once it's closed. So, one of the first kind of ideas for a good enough lock was the RSA algorithm, and it is like this. The key will be just two large prime numbers. So, distinct large numbers. So that will be the key. The lock will be the following information. Their product and some number k. Okay. Some number. Well, in fact, it is important that it is relatively prime. To 5. So this information will be thrown out into the open as the lock. Now the question is how to take this lock and put it onto the box, how to close the box. So that's the box. Let me just call it A. That's the message, that's the answer that I want to transmit. What happens, I can take this lock, N and K, and, well, A in the box, or the lock number A, will be as follows. It will be A raised to the power K and reduced modulo N. So this guy, he takes his message, 42, raises it to this power K, and computes it modulo N. Okay, that's very reasonable. And now he takes, well, that's my message in the box. I claim that it is hard to decipher what it is. What does it mean to decipher? Well, what do people see? They see this number N, they see this number K, and they see this number L. They also know what is the mechanism of this lock. The mechanism is, well, L is equal to A to the power K. And what they want to do is open this box, which means compute A. So, if somebody intercepts this message L, if I know what is L, how would I understand what is A? So to find A, we have to solve equation A to the power K is congruent to L modulo N. Well, we just discussed how to do this. You take this number K, you find its inverse modulo 5n, you raise both sides to the power of this inverse, and now you got the answer A. So does it mean that everyone can actually decipher my message now?
You can compute the order of 5 function.
Yes. So we can solve it, but only if we know what is 5n. But what is 5n? It's not actually that easy to find what 5n is. How do you find what is 5n? Well, basically, we have just one way. You take n, you factor it to the product of p and q, and compute, well, p minus 1 times q minus 1. Well, sometimes it's not that easy to actually factor a number to a product of primes. So imagine that you have a huge number, it's not given as a product of two primes, and you want to factor it. How would you do this? Oh, it turns out that there is there are no fast algorithms to actually do this. There are no fast algorithms that take a number and compute phi of this number, or take a number and compute what are the prime factors of this number. But of course, here, well, this operation is very easy to do if phi of n, which is p minus 1, p minus 1, is known. So everyone right here cannot decipher this message, but the recipient, the one who has the key, who knows what are P and Q, he can decipher it by doing, well, just what we did all this hour, raising something to the power of 1 over k modulo phi of n. Well, so maybe actually let's try some examples, try to actually see the process. So one of the people here chooses the key, and the indicator, well, we will go example. Say 37 minus 137, Q 131. So just choose two large numbers. What you put into the open is their product. So n is 4, 8, 4, 7. Of course, you don't put it into the open as 37 times 131. You just put it like this, some complicated number. And it's not trivial how to factor this number. You actually have to try all prime factors up to the square root of this number, more or less, for faster algorithms, but not that fast. And finally, you choose some more or less random number k. It could be anything. Well, there are some restrictions so that the probability is good enough. I mean, k shouldn't be just 2 or something like this, but if you choose k, some random number, something like this, it will work. And finally, you take your message, that's my a. You compute what is a to the power k modulo, and so you compute what is 42 to the power 277. And you find out, well, here we do have a fast way to do this. We just have to perform something like logarithm of 277 operations. That's not very many. It's not very much. I mean, you just can give it to computer. So we calculate it. Let's see. And you get that this number is 463 modulo 4847. So this computation is easy. Now, well, you keep your computation secret to yourself, but you take this answer and put it into the open. So L is now 463. Everyone knows this, this, and this. And now if you want to actually decipher what the message was, well, you have to solve the equation a to the power a to the power 277 is equivalent to 463 modulo this number, 4847. Well, now we are back to the problem that we know how to solve. If, well, how to actually solve? Compute phi of this number, which is easy if you know the key, which is easy if you are this guy, which is very hard if you don't know. So it turns out 36 times 130, invert this number, 873, so compute. So this number, the inverse of this number is something, 1, 4 plus 3, modulo 5n. This one, once again, is easy to do. It's just a linear Diophantine equations. We have a very fast way to solve such equations. And finally, compute L, this number, cos 3 to the power 1, 4 plus 3 modulo n. You get 42. Okay, so see you next time.